Hi, and welcome to this EMTP webinar study from A to Z. My name is Henry, and I have the pleasure today to demonstrate how to use the transient software EMTP to study the effects of lightning stroke on an electrical network. The first step, which is crucial, is to model properly the network, and you'll actually might be surprised how to model some pieces of it. Thus, I will show you how to build a frequency-dependent model of metal oxide surge arrestor following the IEEE standards, how to create a suitable model of tower which considers propagation of the surge and air gap leaders, how to build a frequency-dependent model of line, and finally, how to include the equipment of substation, including transformers, CVD, conductivity, for fast front transient studies. Then, we will run some parametric studies that will allow you to set all kinds of strategy to design or mitigate surge arrestors, insulation coordination, flashover rates, or the rates of failure of equipment. Finally, we will quickly introduce the corona model that we have in EMTP and which will help you to reach the highest level of precision possible for your study. But before that, let me introduce EMTP to the one of you that are non-user. First, few words about PowerSys. We are the company that commercializes the software, and we mainly deal with the following points: the business development, the sales management, the pre-sales and after-sales front office support, the training and services, the technical support, and the development. Here are a list of references that use EMTP-RB. So, to present you the software, I will go through some very typical example EMTP can be used for. So the first one is the lightning transient. So for that study, we use what is called the Cigre model for the lightning. So it's in the end a current source that model the lightning, and you come and connect this source wherever you want on your network to represent this phenomenon. So obviously here we are talking about a very high frequency phenomenon, and so it's very important to have frequency dependent model for such a simulation. So here, for example, in this case, we apply the lightning at the tower top here. Very close, there is a substation. So usually we don't study really the lightning striking on the substation because they are protecting against that. But the worst case scenario is when the lightning strikes very close to it. So here we put this worst case scenario as the lightning striking the tower top after one span of the substation. So you see locally each span is modeled, and even the tower. Why? Because there can be a back flashover, for example. So it's important to model properly the gap between the conductors and the tower, and of course the footing resistance in case of a back flashover. Because what's gonna happen is when a flashover or a back flashover happen, the surge from the lightning gonna actually travel through the line, and the higher the higher the tower is, the more important it is to model it. So also, as I said, the line here are frequency dependent. It's very important, right? Because the resistance evolves with the frequency, and it increases a lot with the frequency. And if you don't consider that, then you're gonna have a worst over voltage, and the tail of this over voltage after the lightning will be way worse, and you'll end up double sizing your surge arrestor, which costs a lot of money. So that here the model of line are frequency dependent, the resistance, but also the inductance, the zero sequence inductance. All the parameters change with the frequency. Okay, and so we can see here we scoped the voltage at the tower top, and so you can see here as soon as the lightning strikes, the voltage increases, and then we saw those oscillations that result of the propagation and the reflection of the surge through the line. So it's very detailed, and you can see here the energy through the surge arrestor during this event. So those studies typically helps to design surge arrestor, but also the installation coordination, and it's also possible to determine the flashover rates of the installation. Then it becomes kind of a statistical study. EMTP has the capabilities for all that. The second type of example I wanted to show you is the switching transient. It's typically the case of the transient recovery voltage studies. That is what it is here. It's actually a case that I've been demonstrating in a webinar 2 months ago. So here what happened is we want to verify or to design this breaker by identifying the TRV at its terminal. And so in this particular case, what we do is what we call a short line fault. So it's a single line to ground fault very close to the substation. And as soon as this fault happens, we open the breaker. So the breaker gets open, and we can see in green in this curve the inherent TRV at its terminal. And after you can compare this TRV with the rating TRV of the breaker, which is the red curve, and it can be from the standard or the manufacturer, and you can make sure that you have to make sure that the green curve, which is the TRV of the system, stay below the envelope of the breaker. Else there are gonna be some restrikes and reignition, for example. So that we have also a model to represent the restrike, the reignition, and also the arc. But typically for a TRV study, we use an ideal switch. Okay, the next study I demonstrate here is the Ferroresonance. So this is a pretty nice case. Here the engineer that designed this case had fun drawing all the components. So it make it very nice to do presentation, for example, but the model are the same behind those nice drawing. So for the mask, for example, it's something you can edit. Well, we have some symbol editor, etc. So yeah, it's a pretty nice drawing. So here what happened is we energize one transformer, and as soon as this event happened, there is some Ferroresonance that appears in the two transformers. So here we represented the voltage. We displayed the voltage at on the phase A of the transformer, and we can see before the switching, the transformer is in a regular state, but as soon as the switching happens, we have this aperiodic phenomenon, which is at a strange frequency that appears, and obviously it's not very good for the transformer. Also here we displayed the hysteresis curve, because we use in this model an hysteresis, so it's you can see it get very precise. So the Ferroresonance, it's kind of it's a very hard phenomenon to study because it depends on a lot of parameters. It depends on the switching time, on the flux in the transformer when the switching time happens, when the switch happens. Sorry. It depends also of the capacitance of the network, the inductance of the transformer. So it can be very tricky to study, and the best way to do that is actually to do statistical study, even more parametric study. So where you run simulation and change a parameter and run another simulation, and you run like that an entire set of simulation, and you can study the sensitivity of several parameters. So all that can be done with EMTP. Okay, so now we go to something a bit more fancy, I'd say. is the study of the power electronics. So EMTP-RV can do that as well. We actually get in very detailed model because we detail all the switching cells, the protection, the control of those, and so it gets very close to what you have on your network, and it's more than ever a software in the loop, right? So here it's a study of a STATCOM. So we change the voltage at the point of connection of the STATCOM, and we can study the reaction of it. So it gets pretty detailed here. Obviously, for such a study, you have to put you have to select a very small time step because of the switching cell, which is high frequency. So in the same idea, but even more impressive, it's the HVDC. So here we are getting in very huge cases. The biggest HVDC we have it's I think a 301 level. So in that case, you have more than 2,000 or 3,000 IGBTs. It's a huge system. It's highly nonlinear, so it gets very hard to solve for software. But in EMTP, well, we have some benefits that allow the user to run such a case. The first one is the way we solve the nonlinearities. What we do is within a time step, we're going to do some iteration to find exactly where we are on the nonlinear curve. For example, the nonlinear curve of an IGBT. So it helps us to always give a very precise response and to converge in the end. Also, to solve such a case, we use what we call sparse matrix to solve those networks. Obviously, here all the nodes are not connected to each other, and if you have to draw the admittance matrix of a network like that, it will be most of the time 0. And it's like that in most of the network. And so sparse matrix allows the engine to not to consider those 0 and only to perform the important calculation, and it helps to save a lot of time on those huge systems. It actually increases of an exponent 3 the speed of the computation, so it's very important. Here it's a case about transient stability. So it's even if EMTP it's a transient software, it's possible to also do transient stability. It's just a question of the length of the simulation. So we have a lot of model of AVR, of voltage regulator, of governor, and so it's completely possible to do a study like that. So see here we have a fault on a line, and then the line get opened and closed again, and so we can see how all those units, those synchronous machine generator react to that. So we see first the fast transient, and then after the slower transient that result to the governor and the control. Actually, there are a lot of pretty interesting things in that case. The first one is that we see how EMTP-RV deal with the initialization and the load flow. As you can see, this simulation is initialized perfectly. The way we do that is we use the load flow capabilities of EMTP. It's not known, but EMTP have very powerful load flow capabilities. It can be multi-phase and unbalanced, it doesn't matter. So the way it works is for each machine, we're going to link into a load flow, and we're going to specify the power constraint. So here it's a PV constraint. We do the same thing for a slack here. And so then we run this load flow simulation. The software will find all the results. You see here we display the positive sequence. It will find the result, the voltage at every node. And then we run the time domain simulation. It is automatically initialized with the result of the load flow. So it's great to save time. Everything is done by the software. The software calculates the angle of the shaft for the time t equals 0 to start the simulation, and it also calculates the voltage on the field to respect those constraints. So it's very convenient to study the machines and in particular. We can also see that there are two worlds in EMTP. There is the power side, but also the electrical side. See, so that's an example. A control side. That's an example of the control side. So it's mainly transfer function, logic, trigonometry. There is no limit. Okay, here it's an example of that wind turbine. So it's a very typical example. We study the reaction to the wind park to the fault, or also the harmonic injected by the wind turbine. So here it's a post-processing work where we identify the harmonics generated by the wind turbine and we compare them to the standard. So it's kind of a power quality study. So here this case looks like small, but it's actually huge because those are sub-circuit and inside there are a lot of other wind turbines, and so in the end it's 90,000 devices. It's amazing. It's very huge, and again we can solve such a case thanks to the sparse matrix. Another pretty big case here it's just to study a fault, right? So it demonstrates again the capabilities of EMTP. We can see here the DC component of the current during the fault. It's a pretty interesting case. Okay, so the last case, it's the last example I wanted to show you. It's about the protection. So that's something new we do in EMTP. It's the library of relay is actually not available yet. It will be released this year in 15, sorry. So the relay library, we are convinced that a transient software like EMTP is the best way to study protection. Why? Because first, see, when a fault happens, the transient software provides you the DC component, the high frequency, and then the evolution of the current because of the AVR. And so then we can reproduce each step of the protection process. First, the acquisition by the CT and the VT, the current transformer and the voltage transformer, and we reproduce the saturation in them. Then the burden resistance of the relay, and the sampling of the relay with the anti-aliasing filter. Then all the DFT transformation to identify the phasor starting with the waveform. And then we reproduce all the strategy of the manufacturer for the tripping. So it's the most precise way to study protection in the end. See, so here it was an example of the overcurrent protection, and here it's a question of the energization of a transformer. So when we energize the transformer, there is a second harmonic present. So we can see here the current at the secondary of the current transformer, and we can clearly see the second harmonic, and that creates a differential current. And so if we analyze this current, here we do a post-processing FFT, and so we can see the first harmonic level and the second harmonic level, which is pretty high. And this is what happened inside the relay. The relay with the DFT calculates in green the second harmonic during the simulation. So that's a very good way to find the level of second harmonic. The last example is about the distance relay. We also study that. Oh, I actually forgot the last one. The last one is another field where EMTP-RV is more and more used. It's for the open phase detection. This is relative to the nuclear industry mostly. So here it's a case that have been built by the UNC Charlotte, and it's a pretty nice case. Okay, so to conclude, remember that PowerSys offer engineering services for all the presentation, all the simulation and the studies I shown you. So please don't hesitate to contact us if you want more information about that. Okay, So now I'm gonna go through the study of today. So here's the network that we're gonna build together today. So remember, for lightning study, all the models are different than the classic model we usually use for power system study. Here, they all have to be frequency dependent. So if we have a look at the network here, all those lines, the spines of the line are frequency dependent. The towers here are frequency dependent. We'll also model together the footing resistance of them. Then the surge arrestor of the substation, which is here, they are frequency dependent as well. And for the transformer, as I said, it's a very particular model, because for high frequency, which is most important, is actually the capacitance, the surge capacitance of the primary, the secondary, and the mutual of the transformer. Then all the equipment of the substation are modeled by their stray capacitance. So it's a very detailed way of building the network. So obviously here we are talking about very high frequency. The line, the spine of the line, or the length of the line here inside the substation are very short, and so to be able to model and to simulate such a case, we'll have to use a very small time step, something like 15 nanosecond of time step, to be able to simulate that very precisely. So now what I'm going to do is I'm going to build step by step each of the model here. So I'm going to first start with the surge arrestor. Okay, so let's start by doing the model of surge arrestor. So I'm going to create a new file and save it in a new folder. And it will be the high voltage Arrestor validation. Okay, so usually the way we model the surge arrestor for a switching study, for example, we go in the library nonlinear and we have the ZNO data function and the ZNO arrestor. So the way it works is with the ZNO data function, we're going to enter the curve, the nonlinear curve voltage current of the surge arrestor, and this function is actually a filter, and it's going to generate a model of surge arrestor, which is it's an exponential fitting, so it's a quite complex function, and so in the end, this function is going to generate a file, and you load the file in the surge arrestor to be able to use it. So for the switching study, how it works is the manufacturer sometimes give you those curves. It will give you the curve for one disk of the surge arrestor, because you know, like the surge arrestor, they are usually made of several disks. So usually it gives you the the curve for one disk. So you enter here the rated voltage of that disk, and here you write the curve current voltage for this one, and so then here you write the voltage of the rating voltage of the full surge arrestor of your installation. Then here, if needed, you have some extra multiplier. Usually we don't use them, and the minimum current value, which here is 1 milliamp, it corresponds to the MCOV of the system. So we usually don't touch that, and usually also the fitting option. This is those are really advanced options. I don't really recommend you to change those. Okay, so that's how we do how we build a model of a surge arrestor for switching study. But here it's a little bit more complex, because since the lightning lightning strokes are very high frequency phenomenon, we cannot really consider the surge arrestor as a simple nonlinear resistance like it is here. Actually, what we have to do is to consider a more advanced model which has been described in by the IEEE working group 3.4.11, and it's in the end a frequency dependent model of surge arrestor, and it gives a way better response for lightning transient. There are also other models of surge arrestor that exist, and most of the time they use the same tool to generate a nonlinear resistance. So here I will show this particular one, but if you start looking at the literature, you might be able to find more advanced model of transformer that you can build with EMTP as well. So in the end, for this surge arrestor, the frequency dependency is built by those RL filter and RLC filter, and so that's how we introduce the frequency dependency of surge arrestor. So for our application, we have two surge arrestor, one at the primary of the transformer and one at the secondary of the transformer. So today I will build only the first one, and I've built already the second one so that we can win some time. Okay, so here are the characteristics of those surge arrestor. So most of the time the manufacturer provides you the result of some standard test. The most important for us for the lightning stroke study is the test 820 microsecond. So it's a front wave of an amplitude of 10 kiloamp. And so what we're going to do is we're going to build a model of surge arrestor, and after we're going to adjust this model using this test. And so you are sure then to have a pretty decent model of surge arrestor. Okay, and so we will use the procedure described by the IEEE working group 3.4.11. Okay, so to find all those parameters R0, L0, C0, etc., and also the characteristic of those nonlinear resistance, they are actually given by the working group. Okay, so here are the formula to calculate the inductance, resistance, and capacitance parameters. Okay, and after the working group gives typical curve for the two nonlinear resistance, and after you can adjust the inductance L1 to fit perfectly to the result. Okay, so that's what we're going to do right now. Okay, so in this model we have two surge arrestor. Then in the library RLC I bring the resistances and the inductances. We have two of them, and here the inductances. Okay. So the first one are R0, L0, R1, and L1. Sorry. So to change the name, I just double click on the pink, which is the name, so the pink, the word written in pink. Okay, so here it gets connecting here. Then the capacitance here, and I ground everything. So actually what I'm gonna do is I'm gonna put all this model in a sub-circuit, so that after it will be more nice to integrate in the design. and also all the parameters R0, L0, etc. I'm gonna enter them in the subcircuit. So so in the end, the variable will be defined in the mask. So to do that, I just have to enter the parameters here between hashtag, and then I just have to define those parameters in the mask. I'm gonna create the mask right after. Oh, those are L1. In Henry, you have to use, when you use this approach to transmit the parameters, you have to use the standard unit. It's home. Here it's gonna be R0, and here it's gonna be L0. In Henry. Actually, even if I don't select the good unit and I close, and if I open again, it goes automatically to the standard unit. And the last one is C0, and it will be in farad. You can check farad. Okay. So then I'm gonna define, I haven't defined yet the curve of those two ZNO. I will do that at the end. First I will create the subcircuit. So before I have finished to do the subcircuit, I have to add the pin. So for that I go in the tab options, new port connector, and those are power pin. So I can call them P1 and P2, for example. They cannot have the same name. Okay, so the subcircuit is ready. So now what I do to create the subcircuit, it's very easy. I just select everything. I go to options and create a subcircuit. And I can call it high voltage arrestor. Okay, so this arrestor is metal oxide. So the acronym for that is ZNO. So then I can do a nice drawing instead of just a square. So I can put P1 here, rotate it, I right click and I rotate it. I can remove the name. There you go. Okay, just to do something nice. It's always good to have a nice drawing. So then I can put those lines across. Here we go. Okay. Okay, so now I have the arrestor. So I'm gonna define the variable in the mask. So first I have to create the mask. So for that I right click on the device, I go to subcircuit info, to the tab mask, and I mask this subcircuit. So then when I open, it's pretty easy now. I just have to write the name of the variable here and define name. So if we have a look at here at the standard, here are the formula. So what is important is D, which is the height of the arrestor, and N, which is the number of columns of the arrestor in parallel. So here I have only one, and the size of the arrestor is 0.56 meter. Let me double check that. I think it's that. Okay, we'll go for that for now. Okay, so now I'm going to write all those variables. So D is equal to 0.56 and N is equal to 1. Okay, so you can put comments, for example. So here is the 8 of the Arrestor. Okay, and here is the number of columns in parallel. Okay, number of columns. Okay, and so then you can write here the variable you have to transmit. So there was L1, which is equal to 15 multiplied by D multiplied by N in ohm. Then L1, which is equal to 65 multiplied by D multiplied by divided by N, sorry. Then L0 equal to 0.2 multiplied by D divided by N. And C0, which is 100 multiplied by N multiplied by N, yes, and divided by D. Okay. So the inductance are in microhenry. So as well, I'm gonna modify that because I have to put them in Henry. So it will be multiplying by E minus 6. The same thing for L0. Okay, I can put a comment for the first line, just to understand. And for the capacitance, it's the same thing. It's in picofarad right now. I have to put it in farad. Here we go. Okay, and so then I just have to write all the name of the variable I need to transmit. So I don't need to transmit D and N. It's only the other one. So it's L1, R1, and I separate them with comma. Then L0 and R0 and C0. Okay, here we go. So now I'm going to close the mask. The software will give me a message if there is an error in the mask. Okay, so here, for example, there is a message saying that R0 is undefined. So I have to check, and it's true, actually, I have undefined R0. So R0 is 100 multiplied by D and divided by N. Okay, so now it's better. Okay, so now my Arrestor is almost done. I just have to, if I get inside, I just have to create those two resistance. So for that, I'm going to use the data function. So when you create a subcircuit, the subcircuit is automatically locked. So it's in read-only. So as soon as you try to modify something, you're going to have this message. So here I'm going to unlock the circuit to allow editing. Another option is to right-click, go to Properties, and check Unchecked. So now it's done, but before it wasn't, Unchecked read-only. Okay, so actually the best option to find those curves which are standard is to directly pick them from an example that exists in EMTP. So for that you go in File, and you go in the open an example file, application cases, lightning. So by the way, here it's a way to find a lot of pretty interesting example when you want to do study, and there are some nice examples about lightning as well. Okay, so I'm just gonna take those two data function that contain the characteristic A0 and A1. Here we go. Okay. So if I open it, here's the curve. So the data I have to enter here are so basically here you only have to put one, because in our case here we don't use directly the curve from the manufacturer for one disk, so we can put one here directly. But what we have to put here, instead of the desired voltage rating, it's the residual voltage at the nominal current. So it's what the standard called V10. So it's the residual voltage for the nominal discharge current 8/20 millisecond. Okay, so it's this voltage here. So in our case, it will be 1. Okay. Yes, like that. Okay, so then I go to run this case, to the tab run this case. You can have a gap, but usually for the metal oxide arrestor there is no gap really. It's more for other types of arrestor like the SiC, sorry. So here I checked run this case and I can put the name I want. So in that case there was already one name, it was A0. Okay, let's call it A0 characteristic. Okay, and I save it. So you see here in the console that EMTP-RV just built the model. I do the same thing for this one, so I don't have to modify the curve. This one is it's a standard. So I just put 1, and here I put again the residual voltage at nominal current. Okay, so again here it's a special way to build a model of surge arrestor only for lightning. It's for lightning strike. Actually, it's interesting because this model is also valid for the switching frequency. However, for switching frequency, maybe we would rather directly put the curve from the manufacturer if the manufacturer give it. If not, if the manufacturer only give the test of the discharge current, then that's the approach you have to use. Okay, so now I generated my case, so I just have to go in this surge arrestor here, so the non-linear resistance A0. Okay, and I go and select the file I just created, A0, and I load it. And you can see that automatically the design is generated. Okay, I think I haven't built the model here, and that's gonna be A1 charm. Okay, there is one thing I forgot to do before, is to set the VREF. Actually, there is nothing to do for that. It's just click on select default and it calculates it automatically. So I haven't do it for A0, maybe I should. Here we go. Okay, so let me load that again. A0 and A1. Okay, and so this is it. Now my surge arrestor is ready to go. Okay, I can call it actually HVZNO. Okay, and so now what I'm gonna do is I'm gonna apply this nominal discharge test of 8 microseconds, the wavefront of 8 microseconds at a crest of 10 kiloamp. So I can actually, this test have been built already, so I just have to copy it directly. It is built with some exponential. It's not that hard to build it. Actually, you can see here how it is. It's a double exponential, but it's done already. So we just have to copy and paste it with Ctrl+C and Ctrl+V. Okay, so now I'm ready to do the test. I have the current here. Maybe I want to have a look at the voltage at this point. So it's the same voltage at this device. So I go in the scope and I select the voltage. Another option for that would be to go in the meter library and to select directly a voltage scope and to connect it here. It's the same. Okay. So then we are ready to launch the simulation. So I go in the tab Simulate, Simulation Options. So here it's a pretty fast phenomenon, right? the discharge rises in 8 microseconds to a 10 kiloamp. So 1 microsecond, it's a too big, it's a time step which is way too big. Let's put a smaller time step here. So I have about more than 100 time steps to do that. It's good. And in the end, I don't have to simulate a very long simulation because the crest is reached at 8 microseconds. So actually only 10 microseconds, it's enough to simulate this. Okay, so let's simulate it. So here there is no error, so that means we built everything properly. And so now we can have a look at that with either scope view or mplot. Here I'm showing it with scope view. Okay, so first we can have a look at the current. You can zoom on X. Okay, so that's the impulse defined by the standard. And so now we can have a look at the voltage resulting to that. So we look either at the node voltage VZNO, which is the voltage scope we just added in the end here, or we can look directly at the voltage of the current source. They will be the same. And let's zoom on it. Okay, so here we are. So now if I want to identify the maximum here, I can use the cursor here directly or the delta cursor. And so the max is 131, which is a little bit higher than what we were expecting. Right? We were expecting, if I go back to this presentation, we were expecting 116 kilovolts, and in the end we have 130. So the standard actually says that those are standard curve, but after there are some adjustments to do. So the adjustment has to be done on L1. So basically when you decrease L1, that's gonna decrease the over voltage, and you increase it, it will be the opposite. So here I can try to decrease it, for example, to 10. So instead of doing L1 equal 15 multiplied by D divided by N, I do it 10 only. So I decrease it a little bit, and let's run that again. Okay, so we can see it got a little bit smaller now. We're on 130, so we have to keep going down. I think I just did a mistake here, because Pico it's -12. That's probably why I find such a strange result. I'm sorry, I did a mistake on the unit conversion. So I guess now it will be a bit different. Yeah. So I have to do it again. Start again from 15. I'm sorry about that. I didn't convert it well, the units for the farad. So it gives another shape now, which is more. Okay, so we are at 122. So we are closer instead of 116. And so now I can go down to 10. So we go down slowly L1 to reach the good value. Okay. Now we are 118. I'll go down a little bit more, maybe to 7.5. Whoop. And 116.3. That's very good. We can keep this one. We were targeting 116.6. We're at 116.3. It's less than 1% of error. So we can say that this surge arrestor is validated now. Just quickly, something I forgot to mention. Actually, if we look at the actual curve that are given by the standard and the curve that are entered here, you'll notice they are slightly different. The reason is in the standard they give an example in the Annex B in this paper that how to build the actual voltage curve, voltage current curve, and that's the formula to get to apply to find those points and of A0 and the one of A1. So you'll notice, as we said before, we multiply by this voltage V10, but we also divide by 1.6. Okay, so if you look at the curve enter here, they have been divided by 1.6 already. A nicer way to do that, we could have done that, is to enter exactly the same points here for the voltage and put the 1.6 here, and we will find the same result. Okay, so I just wanted to rectify that quickly. Okay, so now we're going to build the model of tower. Okay, so as I said, when we talk about lightning, which is a fast front transients, all the details are very important. For example, when the lightning gonna strike the tower, there's gonna be a surge inside the tower with reflection. So it's important to have a model of tower that consider that, especially for tower higher than 50 meters. So the model we use generally in EMTP is the model described in this paper, and so it's basically an ideal single conductor that we model with a CP model in EMTP. Okay, so the surge impedance of this conductor can be calculated using the formula here, and the propagation velocity in this tower is estimated at 80% of the speed of light. Okay, and so then you can get in even more in detail by representing each span, each section like that of the tower. For the branch, for example, you can use only inductance if they are very short, or you can also use a CP line. And so that's what we're going to build here as a first step. Okay, so I'm going to create a new file and save it in the same folder as the previous one. Okay, so this one will be tower. Okay, so the tower we're going to represent is this one. Okay, so as I said, we're going to use the line CP here. So well, I did the calculation myself, and the surge the surge characteristic is 150 ohm. Okay, so here actually it's a three-phase version of the CP line. I will take the one-phase version. Here it is. Okay, so I select to enter the data as the resistance, the surge impedance, and the velocity. So is this the second one? Okay, so the length of the first span is 20 meters. It's a lossless model, so I put a very low resistance. The surge impedance is 150, and the velocity will be 3 exponent 8. Here you go. So that's the section 1. I don't really need the name of it. Then I'm going to represent the other sections, so which goes by 3 meter, 5.5, 4.8, and 4. So I just copy and paste this one, and I'm going to change the length. So the first section is only 3 meters. I can actually change the drawing to make it smaller, so that it's more representative of the way it looks. There you go. So I update the selected device only. This is when you have when you copy and paste different devices and you modify one of them, you'll often have this option. If you select update selected device only, then this device is turned into a unit type. It can be very important in case of when you have subcircuit, because as you might know, when you have a subcircuit and you copy and paste it different time, all those subcircuits are actually the same object, and if you modify one of them, you modify actually all of them. And so doing that, you make it unit, and so if you modify one of them, you don't modify anymore the other. Okay, so here it's a section of 3 meters, then I have another section of 3 meters, and finally a section of 4.65. Okay, so for the branch I will use an inductance. So I go in the library RLC branch inductance. And so I have a one branch here of 4 meters. So the typical value are 1 millihenry per meter. So it's pretty easy. Okay, again, I don't really need the name, so. And I put the other branch here. So this one is 4.8, and this one is 5.55. Okay, so I unzoom. To unzoom, you press Shift and you roll the mouse. You can also use Control Shift E to zoom and Control Shift R to unzoom. Okay, so here's the shape of my tower. So now we have basically two things left to do. We have to put the footing resistance. So we have a particular model for that, and then the air gap to support the air gap leader to support the phases. Okay, so for the resistance, because of the ionization of the soil, the footing resistance change with the value of the current at a certain point. So for low current, we're gonna have a constant footing resistance. Okay, so in our case, it will be a resistance of 16 ohm. And when the current become higher, then the resistance change with following that equation. So what we're going to do is we're going to build that. Here is a formula to calculate the threshold of the current to switch from a constant resistance to this one. So we're going to model all that. I calculated here, and that's the value. Okay, so what we're going to use for that, it's what we call control resistance. So I don't really remember in what library it is. So what I can do is I can use the filter here. So you click on part by library, all parts, and now you can write, if you kind of remember the name. So I think it was control, here, R nonlinear controlled. It's convenient because there is a drawing as well. Okay, so I connect this device. So the way it works, you have to input here the value of the admittance of that and the value of the current. So for the current, we'll just use control resistance or a control admittance. It's the same thing. So we don't have to, the current is 0 in that case. So I go in the library control and I put a constant here of 0. Again, I don't really need the name. Okay, also I need the current of this going through this resistance to control it, so it will be kind of a loop. So for that I can add a meter from the library meters. So it will be a meter like this one, current meter with an output in the control, or I can directly go in the mask and go in the scope in the tab observe and select current. Now, as soon as I did that, I have here in this bundle, I have the information of the current. To extract it, I just have to right click, go to breakout, and here you can see the current. So I press OK, and now I have this this pin. Oops. Okay, so I can put it here and rotate it. So to rotate, you have the options here with the shortcut. Here we go, and I plug it here. I check the connection, it's fine. Okay, so now I will say there are two types of resistance possible. So either constant or one which depend on the current. So in the end, I will use an input selector for that. So the input selector is here. Okay, I'm gonna flip it to have the input pin down. There it is, and I connect that. Like that. Okay, I can move a little bit all the device, so I do Control A to select everything and use the arrow after to move it. Okay, so let's say when the input selector pin here will be 1, it will be the constant resistance. Okay, so the constant resistance, I said it was 16 ohm. So here actually we want the admittance, so it's the inverse. Okay, can call that our footing. Okay, and so the second input is the function of the resistance that depend on the current. So I will use for that the function of device function of U. Okay, and so this device it's very convenient because it lets you write whatever function you want. So you can use select a pre-built one, or you can create your own and choose the number of input. Okay, so I'm going to choose 2 input. To call the input, it's the U1. Okay, so for example, now I have two pin. U2 will be the resistance and U1 the current. Okay, so if you remember, the function is this one. Okay, so the inverse of this one, because we have to give the admittance. So it will be U1, which is the admittance, the inverse of R0, the R footing. So it's U2, sorry. Okay, and so multiply by the function SQR1 plus the current U1 divided by IG, which is 500. There you go. Okay, so if you want to have a look at what are all those functions that are pre-registered in the that you can use in this box, you can click on the link here, math function, and it opens the help document, which is actually also in the help tab here. And if you go down this document, you will see there are a lot of examples, and actually there is also a tab of everything you can use. It's kind of JavaScript based, so it's very easy to use. If I go down a little bit more here, you have predefined parameters and all the functions you can use. So I just use this one. Okay. Okay, so let me check. I think there is no error here. So So I'm good, and so now I just have to create another function that select the input. So for that I will use as well this function where you can build logic as well with that. So the function of u. Okay. And so this time it depends of the value depend of the selection depend of the value of the current. Okay, so what happened is I'm going to write a condition, for example U1, which is the current when U1 is smaller than the threshold. Okay, so when this condition is true, the value will be 1. When this condition is false, the value will be 0. Okay, so if I leave it like that, the output will be 1 when that is true and 0 else. And so now the other condition is U1, sorry, so the current greater or equal to same threshold. Okay, then the value is 2. Okay, so those two, the condition cannot be true in the same time. So if this one is true, the output is 1 plus 0 multiplied by 2, so it will be 1. If this condition is true, it will be 0 plus 1 multiplied by 2, so it will be 2. So it's in the end, we just build a way to select to select what input. Okay, there are always a lot of ways to do that. You can use also a table function, or there are a lot of ways to do it. That's one way. Okay, so now my footing resistance is ready. So I'm just gonna have after to ground it here, but that's gonna be the output of the tower. So the last step is to now to create the air gap leader. So for that, actually, we have two different models. The first one is a model what we call the disruptive effect model. So in the end, the flashover occurs when this equation becomes true. So when the voltage to the gap minus V0, when the integral of that at the exponent k become bigger than a certain parameters. And if you go in the help, so first you can find this device in the library of EMTP. Okay, so if you go in here in switches, it's the control gap. No, sorry, it's the let me remember which one is it. It's not this one. Air gap. Here it is. It's the air gap. Okay, so if you double click, see it's the same thing. And if you go in the help of this document, there is a tab with where it is. Here it is. There is a tab that gives you some value to enter. Okay, so in our case, we're in the 64 kV system. The length of the gap is 61 centimeters. So here are the value we're gonna use. Okay, so I take this air gap. Here it's for the phase A. So I can call it phase A air gap. And let's put the parameters. So V0 was 276, K is 0.93, and B is 1.1 E minus 1. Okay, so it's from the tab here, this line. Okay, so I can copy and paste it for the other phase. Okay, and I put nice name for all of them, so I double click on the name, I copy this one, and I paste it here. Here you go. Okay, so now you're just gonna have to connect I'm just gonna have to connect this the different line and shield conductor here. But actually what I'm gonna do is put this model inside a subcircuit. Okay, so for that I just have to define the connector. So most of them are power. So for example here it's the neutral, I can call it N, the top. Then here, this one will be the phase A. Okay, and here we have the phase B. Here we have the phase C. I'm actually not sure of the connection, but it doesn't matter in the end because it's just going to be some pins and you can connect whatever you want. You can do manually the transposition of the line. For example, between two towers, you come and connect the phase B on the C, the B on the C on the A, etc. So it's just names. Actually, let's call, yeah, I'm going to keep those names, but you can put 1, 2, and 3 if you want to do transposition. It's arbitrary names. Okay, and so then we have also the ground here. So I copy and paste the power pin, it's the ground. Okay, so now I can copy all that and put it in a subcircuit, and I can call it tower. There you go. So that's not a very nice drawing. Maybe, you know what, we can copy and paste a nice drawing from one of the example. It's always good to have a nice drawing. So if I go, for example, here, I have some very nice drawings. So I just have to copy this one. So I go to Edit Symbol. Okay, here the way they put one in and one out. Okay, we'll do the same thing at them. So I'm just interested by the drawing, so I copy it here. And I paste it. Okay, so now I put the phase. So actually in this drawing there was A in and A out. So what I'm gonna do is I'm gonna duplicate this pin. So you see now I have a new power pin A1, and I'm gonna add them after inside my subcircuit. There you go. Sorry, it's a bit long. I try to go fast. B1. Okay, and C now. And C1. Oh, great. So now we have here we have the ground and the shield conductor at the top. That's a better one. Okay, so I added some pins in the symbol, so I have to add them inside. Remember, when you just created a subcircuit, the subcircuit inside is in read-only mode. So as soon as I try to modify something, I have to unlock it. Okay, so I have to add A1 and A2. So in the end, it's the same thing. It's the same wire. It's just for the drawing, it's more convenient to have one input, one output, but they are directly connecting to one to each other. Okay, so I just put B1 here and C1. Here you go. Okay, so now we've done our model of tower. So as I told you, we have two models of air gap leader. Here I used one which which is the disruptive effect model. We have another one which is even more advanced. It's actually directly the air gap leader. You have some reference if you want to know about this model. It's a pretty advanced model. If you add it, the simulation time will be higher, so the simulation will be slower. We'll still build this model so that you know how to use it and how to find it. So what I'm gonna do, I'm gonna copy and paste this subcircuit. Remember, when you copy and paste the subcircuit, now those are linked together. If I modify one of them, both of them gonna get modified. So if I want to modify only one of them, I have to right click and make it as a unit part. So for that, I go in subcircuit properties and I make the selected device into a unit type definition. I can change the name as well. There you go. And I put in the name. Okay, so to find this model of air gap leader, you can actually find him in the example. I'm not sure it's in the library, let me check. No, it's not in the example. No, it's not in the library, so you have to find it in the example. So it's here in the example air gap leader. Okay, so this example is actually very nice. It shows the validation of this model, so you can have a look at it. It used the Cigre equation in the end. It's a good model. Okay, so I copy that and I'm gonna paste it in our model of tower instead of this. Yeah, the drawing is pretty nice as well. Okay, I'm just gonna put the name quickly. There you go. And the length of those are, we said, 0.61. So that's in the mask. There you go. Okay, so this one is done. In the other one, I just forgot something, is to put actually the input here of the gain, the air gap. This input is just if you want to reset the air gap after, for example, a flashover happened. That's not what we're gonna do, so I'm just gonna put the value 0, like here. So that means we'll never reset it, or it's reset at the beginning, but it doesn't matter. Okay, so the really last thing to do for the tower is to represent the stray capacitance between the tower and the phase, because it has every small stray capacitance like that has an influence when we talk about high frequency. Okay, so for that, I take the capacitance here, non-polarized, and I put it in parallel. A typical value for this is 80 picofarad. So I try this time not to mess up. Here you go. Okay, and I'm gonna put it at every phase. Here and here. Okay, and let me do it as well for the other tower. Okay, and I connect them for the 3 of them. Okay, so this is it for our tower. So now I'm ready for the next step, so I'm going to start to model the entire substation. Okay, so I can close those examples. Okay, and open a new one. I can use the command Ctrl N to quickly open a new one. There you go. And I'm gonna save it. And that will be the full network. Okay, so the first thing to do is we're gonna model, if we remember the network originally, it's not in this presentation, we're gonna model each span of the tower where the lightning strike. Okay, so for that we're gonna use a frequency dependent model of line. Okay, so if I take two towers, so first I will take the first model we built together, can put them here, and I'm gonna model the first span of this one. Actually, see here when we copy and paste, it's written dev. It's not very nice. There is a way to change that, which make it more convenient to use. You go in attribute and you change the attribute. Where is it? Hit name prefix, and you can put, for example, tower. Okay, and so now if I cut this one and I paste, see it's written tower, so it's more nice. Okay, and I'm gonna put a line which is frequency dependent between them. So I go in the library lines, frequency dependent model. Okay, so I'm gonna build this model, and after we're gonna have all the input output needed. So to build the model, we've done that in previous webinars. You have to take the line data. Okay, so let's open it. We create a new case. So the first tab, you don't really have to change anything. So we're gonna have 4 conductor. Okay, if we go back in our presentation here, we have the 3-phase plus the neutral at the top that we're gonna model as a conductor as well. Okay, and so after you have to fill this tab. So to go faster, I'm just gonna copy and paste it from an existing one, and we're gonna comment together the data. Okay, so here we have the number of phase. We don't really say the phase A, B, C because there is no limit. It can be multi-phase. It doesn't matter. So let's say here the phase 1 is the neutral. So you see the DC resistance here, the outside diameters. Then you have the horizontal, the vertical height, and the vertical height at midspan. So all those data are from here. The horizontal, if we set the reference, is the middle. So the horizontal is 0, so that we can see here. The height, it's you add all those together, and the vertical weight at midspan. It depends. If you have the information, you can enter it here directly. If you don't have it, put the same number, and the software automatically estimate it for you. Okay, and then the phase number 2, 3, and 4 are the phase A, B, C, and you have it's built the same way. Okay, so after considering the conductor here, you can do the skin effect correction. So let's put the thick divided by the diameters. Okay, so I modify for all of them. Oh, actually, I forgot 2 of them. 3. Here I have a small unpleasant display. It's actually a small problem we have with this version, but it's actually removed for the next version that goes out. So it's annoying right now, but you will not have it at the version 3.1. Okay. So we are good. Then the model, so we use the frequency dependent model of line. Between 2 span like that, between 2 tower, it's untransposed. So we don't use the balance model, but we use the real T1. T1 is the name of the transformation matrix to create this model. I don't get into the detail. If you need more detail, there are the help documents. But if you want to create an untransposed model of line, you have to select the real TI. And for switching study, you let the software find the model frequency automatically. That depends on the length of the line and other parameter. But here, because it's a fast front transient, we have to specify ourselves the model frequency to have a good estimation. Okay, so I put here 100,000. Okay, so then the length of the line here, so it's the line which will be between two towers, so it's let's say 3 meters, so it's 0.3 in kilometers, and the ground return resistivity 100. That's a typical value. Some of you have more precise value. In that case, it's good. Okay, so then the rest, we don't really have to touch it. Maybe just the fitting. Sometimes it's harder to fit for a very short line. So here I recommend for short line to put a higher number, like 35, for example. It's just the maximum number of pole. It's a mathematical thing. It doesn't change anything with the model. Actually, if you put 25, we can do it together so that you see what happened. Okay, let's call it span 300. So I'm going to generate the model of line. One second. Okay, so see here you have an error, so which means it couldn't converge. So if you have such an error, most of the time just adding the maximum number of pole permitted solve the error, and see now you have ended, it's going well. So when we did that, we just generated a model file named span underscore 300 underscore LVPun, and so that's the one we're going to add to our line. So we click on the line, we go to select data file, and automatically we're going to see it here. Okay, and so now we have the line that take the same amount of phase that we specified here, 1, 2, 3, 4. You can actually display the number if you want to be sure. You go in drawing and you can show the pin number. So oh, I didn't check apply the change. Okay, so the 1 was the neutral, 2 A, B, and C, and so now you can connect them. Okay, so the lightning will strike one of these towers. Okay, so I connect them. So locally, where the lightning strikes, it's good to model each span. Okay, because what can happen is they're going to be a back flashover or flashover, and in that case, you have to model a tower. You model as many towers. The point is the last tower you model shouldn't have any back flashover. Okay, so it's kind of an iterative process. You run your simulation. Here there is a flashover to the last one, then you have to add new. But usually if you put 4 or 5 of them, it's enough. Okay, here I'm going to enlarge the simulation sheets. So I go to sheet size wizard and I put auto expand. There you go. Okay, so I'm going to add some more. I have to check the connection after. There's probably some problem here. Okay, so here it's good, here it's good. Oh, here it's not. Good. Okay, so now I have to ground also my towers. So the ground you can find in the library RLC. I'm gonna connect them better before. I'm not very precise today. There you go. Okay. Okay, so after, when the lightning gonna strike, there's gonna be reflection in between those towers. Remember that the lightning, when we study lightning, it's a local study, it's a local process. And we have to model something after that, but in the end, here you have the rest of the line, nothing will happen usually. There's gonna be no reflection. So what we do to get rid of all those undesirable reflection, we just put a line here, which will be very long. So I'm gonna create another model of line, but this time it will be way longer. So the same characteristic, but instead of 300 meters, it will be 100 kilometers, for example. And this time the model is balanced because we assume that the line are transposed. Okay, and I can call it 100. I'm not sure it went through. Good. Okay, and I go and select the file. Okay, so then here I put a TEVNA equivalent or even just a voltage source of the rest of the network. Okay, so the voltage source, it's a 64 kV. Actually, we work at the frequency of 50. The data we have are from Europe, and this is it. Okay, so to extract the phase, you probably remember you have to go to home, draw signal, 3-phase bus. You draw the bus here, connect it. Always check the connection with the bus. Sometimes it's tricky, and then extract the phase A. So A is the number 2, remember, B, and C. Okay, so now we are done with the line. We're going to quickly model the substation. So here it depends on every configuration of substation. Okay, what you have to remember is you have to model every element. Okay, so for example, that's a short list. Okay, so if you have a circuit breaker, it's 2 lamp stray capacitance of each size. If it's open, it's only 1. So here's a value possible. The CVT are important to model because they have a pretty high value, current transformer, etc. So you have more example in the standard IEEE, a longer list. The best, of course, is always to have the data from the manufacturer, especially from the transformer. It's very critical. Okay, so first, let's say we have a very short cable that connects the last tower with the substation. So this cable can be modeled only with RL. Okay, so we put a value. So that depends on the type of cable. I'm sure you'll have no difficulty finding that. Okay, and so let's say we connect our surge arrestor. Okay, so we have 3 of them, 1 for each phase. Here you go. And actually, you can also model the way they are grounded. So for example, if they are grounded through a cable, then you have to model that as well. Okay, so so you connect all of them here. Then let's say you have a small cable of a few meters. Okay, and then you can actually ground them through the resistance of the substation. So if you know the grounded resistance, all those details, they don't make a big difference, but if you have this information, you're always better to put them, you know. So here the grounded resistance of the substation, let's say is 5 ohm, sorry. Okay, so now we can also do the rest of the substation now. So we did the most important, but let's just as an example. So if you have some cables going through your substation, for example, a long cable of a long line of 50 meter, then you use a CP model which reproduce the propagation. But for a short cable, you don't really need the frequency dependence because you might experience some. That's not the good one again. You might experience some a convergence problem. So for short cable, a CP model is good. So it's the M phase 1, which we take for 1 phase. Okay, so for those cable, you need the length. Okay, so let's say I have one of 50. Okay, again, we use a lossless model, or if you have the resistance, then you can put it. And the surge, you have to know the surge impedance of them. Okay, so here it's just an example. And the speed, it's always the same, about the speed of light. Oh, sorry, we don't see. 3.8. Okay, we kind of run out of time, so I have to go fast. Okay, and for example, we can say that is connected to CVT, for example. Okay, so the CVT, I model it with a capacitor bank, sorry. And the typical value is 4000 picofarad, so 4 nanofarad. Okay. Okay, so also I wanted to model with you a transformer. Okay, so the transformer, you take it from the library, 3-phase input nameplate. But actually, you know, the transformer, this model for high frequency is not valid anymore. Because, you know, a transformer, it's a lot of inductance of high value. But when you get to high frequency, if you remember when you were in class, for high frequency, the inductance are like an open circuit. So in the end, all this transformer is just an open circuit. And so which become important now is the stray capacitance of it. So I still model it here if we want to initialize the simulation at the power frequency, okay, but it's really not important, so I don't pay a lot of attention of that, you know, I put a kind of random value, it doesn't matter. Okay, but which is more important is definitely the stray capacitance. Okay, so I try to put some typical value here, but again, the most precise will be to do measurement or to ask the manufacturer. It's tricky, it's hard to find those data, but it's kind of the only way. Another way is always there are more advanced model. For example, you can use state space device or high frequency equivalent model, but all that it's tricky and it's not really the point of today's webinar. Okay, so this one will be 5 nano. Okay, this one will be 15 nano. So those are typical value. They are from this book actually, so you can have a look at them. And this one will be 20. Okay, and I'm gonna connect it. Okay, so there is not really a need of modeling what happened the other side of the transformer. You can do it, you know, you can put a load, but typically the lightning surge will stop at the transformer for the reason I've said, like the inductance will be as open circuit. Okay, so if we study that part of the network, what happened on the other side will not have a big influence. Okay, but it's still possible to you can do it if you want to have a better initialization of the power frequency. Okay, so here, okay, I did a small substation because we don't really have time, but you can get more in detail like this one. See, where you represent each span with CP model. So here the simulation will be very slow, but it's extremely precise. Everything is represented. So they always, it depends. The more advanced you are in the study, the more into detail you get. Okay, so now we are good. Everything is modeled. So the last part is about the lightning itself. Okay, so for the lightning, we use a concave shape Cigre model. So you can find that in the library sources. If you don't remember in what library, you just go to all parts, you tap Cigre, and you have the current source here. And so we'll come and connect this current source to one of the tower. Okay, so let me ground it here, and you can connect it here. In the same file I opened before, in the example, you can find a nice drawing for this lightning. It's not very important. So then here we're going to parameters the first lightning strike. So remember in EMTP we have an automatic initialization in steady state. So if you can apply this lightning directly at t equals 0, and then you parameters your shape. Okay, so this one is a pretty severe one. You can do more or less, it doesn't matter, it's your choice. Okay, so let's keep this one. Also, if you want to study, for example, subsequent strikes, you just have to put them in parallel like that and connect them. Okay, and then you just change, for example, the time here where it starts, you can put in microsecond, and you can put like that as many as you want. Okay, so once to that point, really, it's just your decision to do whatever you want. You can it's your strategy depending on what you want to do. Let's run this simulation maybe just to see what it looks like. So usually what we are interested in is we can look at the voltage. So let's put some meters now. We can look at the voltage at the tower top. Okay. We can also look at the current through the, well, actually, we can, yeah, let's look at the current through the gap, or even better, if there is a spark, if there is a back flashover. So for that, I go to Observe, and I select the state of the device, and so now the state of this device is available in the control side. So I don't remember we did that in a previous webinar. So to do that, after I take a scope, control scope, and I just have to name this signal. Actually, I will do a copy and paste. It will be easier. So I name this signal. Right click, name S underscore the name of the device. Okay, and I can put it visible. Okay, so I check the tower top. We can also look at the voltage inside the substation. So I put a voltage here so that I can compare the lightning strike with the BIL of all the equipment. Another thing is to look at the energy through the surge arrestor. So let's do that as well. So I had a power meter at the entrance of the surge arrestor, and I just have to take the integral of this signal. Okay, and I can call it energy, and I put a scope at the end. Okay, so let me run this simulation. Oh, I forgot to parameter the simulation. So the parameters, so remember it's a very fast frequency, okay? The time for the lightning, for example, the rising time of the lightning, it's 1.2 microsecond. Okay, so here the time step has to be very small. That's a typical one. Okay. And in the end, we don't have to run the simulation for a long time, because after the tail will be something like 100 milliseconds. So okay, let's simulate for 3 microseconds. Sorry. Okay, remember the power frequency is 50 for this particular example. Okay, so let's run the case. So the simulation is a bit slow, but remember in what level of precision we get now. Okay, so you can open scope view and plot the result during the simulation. So for example, let's plot the energy through some of the surge arrestor. Okay, so to plot during the simulation, I can do it like that, it's nice. So you see the energy during the event. So this is one particular event. It's kind of deterministic approach that we took. That's a very good approach to do, is considering the history or the weather forecast. You can determine the worst lightning strike shape that can happen, and then just apply this one and see what happens. You know, that's one way of doing it. And so then when you identify the over voltage, can after calculate the probability of chance of failure of an equipment considering this voltage, and so like that you have the rate of failure of your substation. Okay, so we can have a look as well at the voltage on the tower top. I'm going to put it on the page 2, and on the substation. Okay, so that's a kind of study we can do. Okay, so let me now maybe quickly show you how you can do a study considering what you want to do. Okay, so I prepared those files already because we don't have time, but we can do some parametric study if you want to see the influence of some parameter to the result. Okay, so the first one, for example, why we would lead such a study if the goal is to see the maximum the maximum amplitude of lightning before the power, the energy through the surge arrestor reach a certain level. Okay, so for that we can do a small parametric study. So the way it works, the parametric study in EMTP is we write a small script for that. It's very easy. So first you have to copy and paste like that a block. You can change the drawing with the edit symbol, it's not important. What is important is when you right click, you go to attribute, you have the attribute is script.open.dev that has to put the name of one of the scripts that has been written before. Okay, so here the script is open next to it, it's in the same folder, so that's why I don't have to put the path. So yeah, the extension DWG is the format of EMTP. It's, you know, when you click on Control N, you can create a JavaScript. So it's the same thing. It open a DWG. Okay, so far it's in the same folder. As soon as I double click on this device, I'm gonna run this script. Okay, just to let you know, right now we have to do scripts. That's not the point of this webinar to study parametric study. But I'm going to do a webinar on that in the future. But we are modeling a new tool that is extremely powerful for parametric study. So I will wait that this tool is released before presenting it. Okay, so quickly how it works for the parametric study. So it's the script that is called. So I advise you to start with this one and just to modify it. So here I put the name of the device that I want to do the parametric study on. So it's this one here, you see the name is lightning 1. Okay, and so then I create some vectors of all the value I want to give. So there is the amplitude, the reset time, the max lobe, the tail time, that's your choice. And here I'm going to do 5 simulations, and here are the value of the 5 simulations. Okay, because we don't have much time, I only do 2 simulations. Okay, because so remember, that's one way of doing it, but it's a script, so you can do basically whatever you want. Okay, so here they're going to take those 2 value, so it will be a very short simulation study. And here after you have to write the name of the scope you want to save. Okay, so for that it's easy. It's just once you run the simulation once. Okay, I did it previously. So you open it with a Hemplot, for example, and so if you want to have a look at the energy through the surge arrestor, you plot it, and you have the name here. Okay, so you just have to write the exact same name, and that's what I did here for the phase A, B, and C. Okay, so then in the script, so there are not much stuff to modify actually. Just here in my case, what happened is at the point, if you have a look at this attribute, all this data, okay, if you go in the attribute, they are all saved in the attribute named params A, which is here. So what I did, I just copy and paste this in the function set attributes here, okay, and instead of putting the hard value, I put it the vectors. So at each simulation, I change using the function set attributes. I change the value. The input of this file. Okay, I go quickly on that, but again, after those files will be available for you, you'll be able to look in detail. Okay, so I save it and I run. So to run that case, I just double click on that. And so you can see now the simulation value where the amplitude is 70, so now it's running. You don't have to do anything. You just have to wait. So I just did 2 simulations here to go faster, but you have no limit. You can do like you have no limit. And actually, in the future tool we are developing, use the different cores of the computer to run all the simulation in parallel. So it's a very systematic way. Okay. So in the code written here, you only save the minimum, maximum value. Okay, so it's a good way to design. We don't save all the data, all the results, because it will be too much memory consuming. Okay, it's actually an option in the script. I'll share this script with you, and so you'll be able to go through it. But there is actually a line that has been disabled where you can save all the data, but it will reach very fast the limit of your computer, depending of the simulation and the number of data you save, obviously. Okay. Okay, so while the simulation is turning, it takes a little bit of a time, but it will be finished soon. I can quickly show you the Corona models. Okay, so this one is in the example. So if you go to File, Options, Application Case, you have here the Corona. Okay, so the Corona, the way it works, it's see here we model a line, for example, and so even within the span, if you go inside, within the span you have to use the device Corona that is, I think, in the library. Yeah. Okay, so you have to use this device and put it in every small section. It's actually every 25 meters. Okay, you put the Corona, and if you look at the help from this device, okay, so it explains everything about the model, but also the validation, and that's the interesting part. Okay, so it shows how to use the model, to put it every 25 meters, etc. There is also the equation, so it's very very advanced. And after, so this model, like most of the model in EMTP, have been validated using comparison between measurement and result. So here you can see the measurements, which are the surge here. So what happened is there is an impulse through a line, and we look at the surge traveling through the line. See, so the measurements are those, and these one are the one given by EMTP. So this is without the Corona. Okay, so you can see for when you study locally a lightning strike, it doesn't make any difference. But if you want to study the traveling, then it's not correct not to use the Corona anymore. Then if you use the Corona, see the results are way better. So it's actually pretty impressive. Okay. Okay, so actually our simulation is done. So we can have a look after. As soon as you run this simulation, so everything is written in the script. You go in the underscore PJ, which is always generating when you run a simulation, and you are going to have this file here that has been generated. Okay, so if you click on it, it's just an Excel file. Open here, and it gives the value of the here I asked for the energy through the surge arrestor, and it gives the value for the different types. So you can lead like that 100 simulation, and you'll have all the value you want. Okay, so it's a pretty good. It's very easy to do. I let you try that, but it's very easy to do. Okay, though, so this conclude the webinar of today. I really apologize about the length. I've been a little bit ambitious about this one, but anyhow, if it was too much information today, don't worry about that, because as always, this webinar will be posted on our YouTube channel. So you go on YouTube, emtp.com, and you click on our channel, and you have the previous webinar we recorded before, and we're gonna add, actually it's already online now, the new webinar. Also, the content of this webinar will be available for all the customers. So you just have to go to EMTP.com, you go to the Exchange platform, okay, and you're gonna have here the content of the webinar. Okay, you can also request it to me by email. You have my contact information. You just send an email to sales.usa@emtp.com. So once again, thank you very much for attending this webinar. I really hope you enjoyed, and I wish you a good day and enjoy your use of EMTP. Bye.